trying to talk about place by ear, and it's getting all the way digital. And here's how it works. You guys hear like, in our system is a decimal system, so we go use tens. Others, computers are binary, so they use twos. The color part of computers is hexadecimal, so it's 16s. The sexagesimal, which we talked about, is 60s. So we'll start with decimal because that's what we're used to, mostly. And that is, you get your first column when you first start counting, and that's sort of your ones place. 79. And then it rolls over to your next one, and that's your tens. And then you get your next one, your hundreds. And then your next one, your thousands, and so forth. Binary is the same. You get the first column, which is your ones, or we call this the units. It's just a standard way of doing it. And then the next one is going to be your twos. Your binary number is going in twos. And then it's going to go in four terms of power. So then your fours, and then your eights, and then your 16s, and so forth. Decimal, so case 20, that would be your ones, and then your 20s, and then your 400s, and so forth. Sexagesimal, there's 60, and then you get your units, 60s, 1 example, 600s. And two place values you got opposed to it is will be counting change or change. I could just hand you a whole bunch of change.
It would be like me handing you a bunch of change and go, here's a bunch of change. Even though it's quarantine, there's not much like change out there, but it used to be like you can hand a bunch of change. And how much is in here? And you gotta sit there and count through all the pennies and the dirty. It's just a pain to know how much it is. And then otherwise, if I hand you a change drawer and say, hey, and everything's organized there, hey, how much is this? And you go, oh, no problem. And you count out like the pennies and the dimes, and each time you can count them up, add them up, multiply them by the number, and put it all together. That's like having place value, and way better. Cool.
So, real quick, we're gonna go over some number-based systems, most particularly the Babylonians and the sexagesimal system. The Babylonians were modern-day Iraq, Tigris and Euphrates, King Cyrus, all the way up to Nebuchadnezzar. Some good history to learn there. And an interesting facet about their awesome mathematics is they were base 60, like I said, and the base system we're base 10 because of this. It's sort of it's a commonality, and that's been around and agreed upon. There's no other real reason why. The Mayans, they were begesimal, that's base 20, and that's most likely because of fingers and toes. And the Babylonians, they were base 60, which is way cool. And it turns out for lots of reasons, and one of them is the way that they think you could count on your hands is, or maybe here I can look at it. So like I got like 1, 2, 3, and then before I'd have like 3, 6, 9, 12. And now on the other hand, I can count some of those 12 off, like 12, 24, 36, 48, 60. And just my two hands, I'll be able to count off to 60. And with some basic memory, we could do 60 60s and then we're up to 3600, which is way cool. And another facet of 60 that made doing business, because that's why they were focused on doing math, that was their MO for sure, was tied to this kind of number of other things. And the fact that 60 can be broken down, so let's say we're gonna break it apart by 15 and 4, and we're gonna keep finding numbers that go into those as we go. Right. And so we got these numbers down here. And this is the prime factorization. So if we have 2 2s, a 3, and a 5, we'll get 60. If we have 60, we'll get 2 2s, a 3, and a 5. It's a combination of numbers such that the order doesn't matter. It doesn't matter in which direction we go or however we get to those 2 2s, 3, and a 5. It's just the fact that we have this. And this fundamental theorem, which is created, sort of attributed mostly to Gauss, but Euclid has it, just wasn't formalized enough, I guess. And he probably picked up enough on it from beforehand. Simply stated that every number, like whole type number, has its own unique prime factorization. And if you have a prime factorization, it's tied to that. It's like a key. So like, let's say I have like 45, right? And break that apart, 9 and 5, and 3 and 3. Well, if I have 2 3s and a 5, I'm gonna get 45. Or about 45, I'm gonna get 2 3s and a 5. And now we've broken it down to the parts that can't be broken down anymore. And that's also ways we can rearrange it in all the different ways we might want to. 60 is kind of special in that regard. So 60, you know, we got like 2 times 30, 3 times 20, 4 times 15, 5 times 12, 6 times 10. Sorry, my numbers are getting kind of small. And that's a lot of different ways that we can parse it down and break it apart, which is really useful. And for the Babylonians and their ways about going about mathematics, that was perfectly well enough. They could figure out the numbers they wanted to figure out. For instance, if you have like a square of area 2 square feet, or whatever unit that they use at that time, rods, or I don't know what they use. Before that, though, I do have a question that we should figure out, and this is would be the assignment regarding the factors. So consider the natural numbers, 1 to 100. Those are like the numbers that you count with as the first start. The whole numbers have the 0. Which element of this set has the greatest number of factors? You know how like 60 has a whole bunch of them? Well, which one, 100, between 1 and 100? So we're going to move into the next question real quick, because it'll make things make more sense. We had the previous one, right? And now we're going to have to construct a square with 2 square units, something new. Not really going to talk much more about how you're going to go about doing that. That's just on you. We're going to look at some stuff, and all the information should actually be there then. Ah, cool. And having an area of 2 square units is an interesting concept. So we got 2, maybe we might do inches squared, right? So like it's got some amount on each direction. And well, we want to know how long these sides are. And if you think about it, like if it's a number squared, right? Some number times some number equals 2 inches squared, right? This number times itself has to be 2, right? Well, 1 times 1 is 1. And 2 times 2 is 4. So it has to be between 1 and 2. So maybe like 3 over 2. 3 over 2 times 3 over 2. That's 9 over 4. And in case you need to review, if you want to turn that into a mixed number, so 4 goes in 9 2 times, and you got 1 left over, right? So 1 over 4. So a little bit over 2, we're getting closer. So 3 over 2 is closer than 2 was, right? But we could keep doing that, and we could keep doing that forever, and we would never find a conclusion to it, because the fact of the matter is irrational. Which is kind of, to some people, not that big of a deal. To 2, and remember we just did the fundamental theorem of arithmetic, and one thing about that is we can use it to identify square roots real well. So like, let's say you have a number like 16, you can break it down, and it'll be 4 2's, right? Well, whenever you have a pair of things, you're going to do a square root. So like the square root of 16 would be that broken all the way down, and whenever you have a pair, here we end up with 2 pairs, right? So all those come out, so we come out with like a 2 times 2, which is 4, right? Which we know that square root of 16 is 4. Or the square root of 64, but that would be a bunch of 2's and stuff. Now that same thing holds true too if it's kind of a wonky number like 12, you know? So if you got 12, you're going to break that down. And we get there, right? Now we already talked about we had a pair, right? So the pair will, as a square root, like 1 times itself, obviously, is no longer a square root. We're done with the symbol. But these numbers that are just hanging out, that are not part of a pair, those stay there. And we're still stuck with this thing, which there's ways around it. But we're times the Greeks, and the fact of the matter is, like the universe had to work in harmony, and all things have to be rational. And for that, it means it's like a rational number is a number that can be written over another number, like 3 over 5 or 7 over 9, or just no wonkiness to it. It has to be able to be written like that. Well, they insisted it had to be, and everyone was like, no, you can't be. Well, not everyone, but you can't be, because you just can't be. And Hippasus proved it, and they killed him. And later on down the road, Euclid, he proved it again, and I think they listened to him. I don't know. Sort of. You can't get away around it. And so he did a proof of reductio ad absurdum, which means we're going to start out by saying this is true. The square root of 2 is rational. It's written as a ratio of a number over a number. Cool, right? Well, let's do some rearranging. This is more algebraic. Well, the inverse operation of square root, and it being, and the inverse operation of square root would be to square. So we're going to square both sides. So 2 equals, and squared over d squared. And now we're going to take this number that's down here on the bottom, and when there's no like addition and stuff, if it's just division down there, we can just bring it up over here, and it would be multiplying on the other side, right? So it's like inverses. This is more of the algebraic way. You could have some, who knows, way of writing it out. And the algebra is really the Arabic's contribution to mathematics big time. You know, the Indians, so much with the V.I.P.N, that's where we get the Hindu Arabic numerals. So we have all this going in play. It's cool. Well, we can kind of expand this out a little bit more. You know, d squared would be also d times d, and n squared would be n times n, which is kind of useful. Now, if you remember back on the fundamental theorem of arithmetic, like a number can be broken by factors. Like it has so many factors that it can be. And that number of factors can either be even or odd. There we go. That number can be even or odd. And that's the only way it can be. And the thing with that is, well, if you double any number, even or odd, you always end up with an even. Think about it and you'll find that out. Right, so we're going to double a number here, and if we double it, it's going to be even. And we double number of factors over here, is going to be even. But wait, there's one extra one over here, so the even now has 1 plus 1. Even plus 1 is odd. And that cannot be, good friends. And so therefore, this number must be irrational. QED or whatever it is. Blah, blah, blah. And now let's go solve some new problems. Here we go. I don't know why I'm not just having fun with it. Hey y'all, we're gonna make a peace crane. Right on. First off, it's quarantine season, so you might not really have any origami paper on hand. If you go to the art supply store, that's just you get some cheap, and it makes your folding really fun. But this is cool to use things you got around. I got this magazine. This one bit. We got plenty of projects you can do with old magazines if you got them around, but it doesn't really matter. Now you got the sheet, and it's not a square. So we need to make it square first. So the thing to do is you take the short side and you line it up with the long one. And when you're folding, the thing to do is make sure you line it up real good before you crease it. Because you can't really uncrease paper. You can kind of redirect the crease, but you can't really undo it. So make sure you get it how you want it to do it, and then you come back. Oh wait, no, we need a square, right? So as it's over there, we folded it over there. There's this piece over here, and you turn it over. And you can fold it back like such, and it'll line up evenly there. That'll be a right triangle, and because the two sides are the same, it's actually a 45-45 right triangle. And this one becomes really important. It's an isosceles right triangle. One of the most famous triangles there is, if not the most famous. Anyway, when it's also half a square. It's half a square, you know. Well, we can see that, and that's where the diagonal, and that's kind of where this whole square root of 2 stuff came about. We can actually see it here, which is kind of cool. But I come back, and, you know, fold it back and forth. This piece right here that we made in a square, that's the one I want to tear off. You might lick it, you might do whatever. And you want to start slowing down. Just take your time on things. We're going to make the bird base. There's 2 main origami on the bird bases. This one, and as I'm going to do it, I'm going to try and tell what a little bit else I know about history. So you fold it like that, and then you do it like so. The other catty corner was. Origami pretty much started as soon as paper started. The Chinese, something like 600 AD. Or something like that. And then, perfect, so do that. And then we're going to turn it over before we do it the hamburger hot dog way, which is funny to say it this way because there's no one or the other. It's
just the side to sides. But definitely turn it over, it'll make a difference. And notice how I'm lining it up before I crease it. Alright, open it up. And we do it the other way too. Same direction, lining it up. I'm missing somewhere, but it'll be okay before I crease it. And now we got it like so. Obviously there's lots of geometry lessons here. We could talk about it all day long, but we're just gonna focus on trying to make a bird. And the way you want it, see how it's kind of poking up like this? As you see a square here. And that's the thing we're trying to find for the bird base that we get to, like so. And it should close up nicely. One more time. And if it does it, you got it right. You might have it flipped over and backwards. So we got there. And we're gonna take, you gotta notice we're gonna focus with this bottom side that's got a little opening, not the top like that. We're gonna take a side, we're gonna line this line up with the one in the middle. But, so the Chinese developed it, and they kept it like ferociously secret. So during the era of the silk routes, which is where, like when the Romans and stuff bought all kinds of silk and funneries from China via Persia and India and Tibet and all kinds of things, they really like to get paper. And we're gonna do that on all the sides. And the Chinese would not let that go, but also towards the north, east, towards Korea. It did get into Korea. I mean, that they do share a lot of alliances there, and they definitely did want it to get to the Japanese. But there was a Korean monk, a Buddhist monk, who was friendly with the Japanese, and there was people in Japanese culture. So now we're going to take this part and fold it like so to give it this here. We're doing it to give it actually a crease. Converted Buddhism, and he brought with him the knowledge of making paper. Now, and the passage of making paper and origami from since then, I was talking and not even, so we have it like this, and this is kind of the key spot of a bird base. This is where you pay attention. We fold it back and forth, we got it like that. We opened all these up. Now you're going to take this top one and go all the way back to that crease that you made. And part of the trick a lot of times on this one is you got to fold back those creases that you've done earlier towards the top. And sometimes it doesn't quite want to work out, so take your time. And if you get too frustrated, just ball it up and start again. Which you don't do, just give up on it, right? Give up. And we do that to the other side. See there, this spot right there. Well, and then Japanese in their society, for the paper folding really was something very just utilized within the culture. And early on, there became this legend that if you folded 1,000 of these cranes, these peace cranes, 1,000 of them, you could get a wish. Now, we're going to do the next one. At this point, if you do the next set of folds, you'll end up with like the normal crane, people standard piece crane, and it's very pretty. And if you don't, but if you follow through, you'll end up with a flappy look. It's not quite as pretty, it doesn't have quite the same lines, I think, but you might have your own, but it does flap. That's cool. So if you want to do this, you don't do this next step. If you do want it to look like this, do this next step. Now if you're doing piece cranes, then you gotta do this next step. You take this side, fold it in, well, that's quite a good legend. And it came that the U.S. decided that it needed to drop atomic bombs on Japan and kill like lots of people all at one go. It doesn't really matter whether or not that was the right decision or not in some ways, because it was a decision that happened. So we must just learn from everything we can. Well, like most of the parents and everyone died in Hiroshima, and there was kids who just kind of grew up, and one of them was Sadako Sasaki. I had to double check. I wrote her name down, but it's not my native, so I'm definitely probably jacked it up. But she caught leukemia because of the bombs. Now, this next step, that was the step you would do if you're going to have the normal crane, and not do if you're going to have the V.I.P.N crane. And here you're going to do this on both sides and fold it up. It doesn't quite matter your angle. I generally do it sort of lined up with that. And the inner part goes all the way to where it separated it. And on each side you're going to do what's called an inside reverse fold, which is a cool name. You open it up and you fold it, and then you fold it like sort of reverse on itself. It goes up, boom. And here it's fun because it always seems like it might not work, and if you get it, it just kind of falls into place. Here, you might have to get these sort of work in there. The piece crane is not the easiest thing that they of origami. It really is something to do, and you always have to pay attention to it. And one of these head and one's the tail, it doesn't really matter. I tend to personally try and figure out which one is more messed up. Like this one's torn here. I want to make that one the head, and you fold it down. So this may or may not have been a good idea to choose the torn one. We'll see. It'll do though. There you go. Now Sasaki, she caught it, and she had some really good dear school friends. One of her missions before, her goal was to make her 1,000 cranes, and I don't know if she actually completed it or not, but her school friends carried on her legacy before they still do it, and they bring it all around the world. It's really aimed at to the youth, and the idea that for peace, you're making these, they're just made for peace, and the process of doing it seems silly in a weird way, or not silly, but very minimal. It's just a sheet of paper, but you do them, and I have not done 1,000 of them yet, but each time I really do complete one, there's something that does kind of feel better about it, and there you go, you got a crane.